Hello friends, I welcome you all to this video. We are with chapter 5 of microwave engineering, the family of avalanche transit time devices we are dealing with. So in this particular family we have gone through so far with the meaning of what exactly the avalanche transit time mean. The family is introduced there and we started with one by one the devices belonging to this particular family to generate the microwave energy based on to the principle of negative resistance. So after completion of the read diode, impaired diode, addressing and practicing the two problem statements onto the impaired diode, now we begin to understand what exactly the second mode of operation for this particular type is, that is TRAPATT diode. So here we start with our topic that it is TRAPATT diode. So TRAPATT is basically the abbreviation for it is trapped plasma avalanche triggered transit device. So meaning is that this particular device is making the use of transit time along with the effect of avalanche. So it is very clear that the avalanche effect is possible when we have a junction into the semiconductor material as a substrate of the device, and that junction is operated into the reverse bias mode. So here we have the avalanche effect making the use of transit time also, and because of the avalanche effect, whatever the free electrons that have been formed because of the avalanche multiplication, we can say there it is some kind of trapping of that particular plasma. Hence the device is called as trapped plasma avalanche triggered transit time device or transit device called as TRAPATT diode. So it is basically derived from the earlier that we have gone through, that is impaired diode, basic structural diagram for our case of TRAPATT diode we shall be considering here. So typically it can have the structure of P positive connected to N, it is further connected to N positive. The substrate may be of silicon material or it may be of gallium arsenide material also. Now considering a simple structure, we can have the structural diagram as here we make the three parts corresponding to three semiconductor type materials. First is P positive, then next is N, and next to that is N plus here. So the subscript plus is representing the high doping level. So here it is the P type, heavily doped, so it has majority of carriers in more number to be the holes here, whereas for N type we have a generalized doping profile, so it has the majority of free electrons, and here as compared to this N type it has more doping into the N positive, so heavy amount of free electrons being the majority charge carriers are present into the third domain here. Now we can be using this particular structure with the help of reverse biasing, hence we can make the connections to this diagram as here we provide a supply to the P positive and negative 1, and the next connection is to the remaining electrode here. So here there it will be a square wave representing the current flow here. So I can mention here square wave current drive. Now as far as the dimensions of this particular semiconductor materials being the part of the TRAPATT diode are there, we can have the first heavily doped P type that is represented as P plus of the dimension range 2.5 to that of 7.5 in terms of micrometers, whereas the middle one, mostly the drift length, that is of 2.5 to 12.5, again micrometer. So as we have a reverse bias here, this is basically the depletion layer. And here the cross-sectional dimensions, if you take the cross-sectional dimensions, can be of 50 micrometer for the case of continuous wave operation, or it may be of 750 micrometer for the operation into the low frequency mode having the high peak power. So this is the generalized structure we can consider for the TRAPATT diode. So as we have gone through the diagram, a simple P positive N and N positive structural diagram we have taken for the example of the TRAPATT diode here. The PN junction here is operated into the reverse bias, and while having the operation of the TRAPATT diode, the current densities that we have shown here, the current drive, are well in excess of the amount those encountered into the normal operation of the device. So this is the difference as we are working with the TRAPATT diode. Further, because of the reverse bias here, there it will be the high field domain generation. So the high field avalanche region that will be developed here into the N-type material will be propagating through the diode body, and it will fill the depletion layer. See, the depletion layer we have shown for the entire N region. So it will be completely filled because of the avalanche plasma generated here, and it will be trapped inside the low electric field applied region. Hence we can name it with the trapped plasma avalanche triggered transit time device here. Now further operation of the TRAPATT diode can be taken with the help of a graph here. So this graph is corresponding to again the same structure that we have discussed before. The first semiconductor material type, it was P plus, the middle was N type, and the last was N positive here, and here it was the applied field or the applied supplies to the diode so that it can operate into the reverse bias mode here. Now in this particular graph, onto this horizontal axis we take the parameter of time. So time we represent with the help of T. We start at 0, and here we can take the complete transit time tau. So it has various shifts from this point to this to this to this point, this, and back to this particular level which is at equal level. So on the vertical axis, this level is corresponding to the either you take voltage or you can take the current. So while the device operation takes place, the charge carrier completes a time duration from 0 to tau. It will be at the different levels of either voltage or current. So these different levels or the points into this graph, that we can make a nomenclature here. Let us say at the 0 it will be at the point A. Next to that, after a certain time duration, it will be attaining the level of point B. After a reduction into the voltage and current levels, it will be at point C here. Next to that, the reduction continues until there it will be the achievement of the position at point D. Then it will be a gradual start to have increase into either the voltage or current, and we go up to the point E, further the point F here, and next to the point G, and which will be making a constant here up to we get back to the point A. So a lot of changes into the voltage or current levels we observe into half of the portion of this transit time. Hence we mark here tau divided by 2. For rest of the half cycle of the transit time, we have the constant levels of voltage or current denoted here. Now as we shift from point A to point B, basically the operation whatever it happens to be in the device that it is, we summarize in this particular diagram, that is called as charging of the device. From B to C, here we write it is the formation of plasma. So I mention here plasma formation right from B to C. C onwards up to the D, here we can represent in this diagram, and from D to E it will be of the plasma extraction. Next to the plasma extraction, we have the residual extraction, and lastly from F to G, there it will be again a charging here. So these are the various stages we shall be discussing here. So here we shall be detailing the discussion with respect to the operation of the TRAPATT diode. Now we start at point A. At point A, the electric field which will be represented in terms of the voltage per meter. So electric field generally represented as volts per meter. So it will be directly proportional to the voltage or current you can take. So electric field will be basically the uniform in the body of the TRAPATT diode, and it will be but less than that is required for the avalanche breakdown. So with respect to the different positions denoted by A, B, C, D, E, F, G and back to A, we shall be continuing here. So at point A here, the electric field that we represent generally as capital E, as just now we have denoted onto the figure, will be uniform here throughout the body of the device here into the semiconductor platform, but it will be somewhat less than that is required for the avalanche operation. So this will be the position A here. Now during A to B, what happens we shall be discussing here. Now there it will be a thermal generation inside the body of the semiconductor, and because of the thermal generation, we can say that it will be the happening of charging of the diode. Hence from point A to point B, the electric field that will be rising here, or in terms of voltage or current you can say there it will be rising here. So this charging or the thermal generation will be more than that of the breakdown voltage. And after the breakdown voltage, there it will be the effect of avalanche. Hence after point B, we will be having the curve segment denoted as BC into the diagram, due to the particle current exceeding the external current. The electric field that we denote with the help of capital E will be depressed throughout the depletion region. So in the diagram, the depletion region has been shown to you people. So there it will be a depression or simply a decrease. Therefore B to C, there it will be a drop down inside the curvature that we have shown in the graph here. Now during this particular time interval we have shown from point B to point C here, there it will be the formation of the dense plasma, and this dense plasma that constitutes the free electrons as well as the holes we can see here, they are present when the electric field is at low potential, and finally plasma will be trapped inside the depletion region. Hence we call the device to be the trapped plasma avalanche transit time device, the TRAPATT diode. Now after the point C, we have the curvature segment denoted by C to D. During the time duration point C to D, there will be some of the holes that we can represent here, and some of the electrons from the plasma, they will be having some amount of drift, so that they can be having a decrease into the voltage up to the point D. So there it will be a drift here, and rest of the plasma will be completely trapped here. So this is actually the trapping up to the point D that you can see into the diagram here. Now whatever the plasma has been trapped there it is a necessity that the residuals of the plasma should be removed from that particular place. Hence, as we proceed in the graph, you find the curve segment that it is DE. So from D to E, there it will be a removal of plasma from the depletion layer, and still some residues of the electrons will be remained in one side of the depletion layer, while the residuals of holes will be onto the another side. So this will be the situation as we come up to point E here. After point E, there it will be the curve segment E to F. So in the curve segment E to F, there it will be the residual charge, and that has been completely removed, while we have an increase into the voltage or the current you can take. After this particular curve segment, we have the curve segment denoted as FG here. So from point F to G, the diode will be charging again as a fixed capacitor, and from point G to point A, there it will be the diode current, and it will be going to the zero for the fixed capacitor for the half period of the transit time that we have shown inside the diagram here, whereas the voltage will be maintained at the point A here, and this particular cycle will be repeated further. We get back to the diagram here. So whatever we have discussed, from point A to B we have charging, from B to C there it will be a plasma formation, from C to D and then D to E there it will be the extraction of the plasma, the removal, the residual removal will be there. From E to F again we can be having a charging, and from G to A there it will be the constant voltage, but the current will be dropped to this level, up to zero level that we have shown with the help of these dashes. So this was the operation of the TRAPATT diode. Now as far as the device operation is concerned, there it is a very important role of the electric field, so that when it goes to the low potential level, the trapping of the plasma constituting the charge carriers will be there. So the generalized electric field as a function of the distance here we can denote mathematically by the equation. So capital E as a function of distance x, and it will also be dependent on to the time parameter. Hence I represent E as a function of x comma t. So it will be equal to the maximum value of electric field denoted by EM minus, here we have Q into capital N suffix A divided by epsilon suffix S, and it will be in multiplication to the distance measured by x parameter here, and it will be finally added with j into t divided by epsilon suffix s here. So here capital N suffix A, this is nothing but the doping concentration of the middle N region, and rest of the parameters, this is the electronic charge, this is the maximum electric field, this is the cross sectional current density, time t as a parameter, permittivity of the semiconductor material are denoted here. Now the exact time at which the electric field achieves its particular maximum can be given by the formulation T is equal to, we can have the electronic charge in multiplication to the doping concentration of the N region divided by the cross sectional current density J in multiplication to that of the X here. Finally, whatever the avalanche zone has been formed inside this particular depletion layer, we can formulate in terms of avalanche zone velocity that has been represented as V suffix Z here. I name it avalanche zone velocity, and this is expressed in terms of the derivative of the distance x with respect to that of the time here, or it can be expressed as the ratio of G divided by Q times the doping concentration N suffix A here. Next to that, in terms of the time here, we can say here the transit time of the carriers. Transit time of the carriers can be denoted by tau suffix s, and it will be the ratio of the drift length capital L divided by the velocity v suffix s. So here v suffix s can be called as a saturated carrier drift velocity, and capital L has the same meaning, that is of drift length. So this completes the understanding of the device operation TRAPATT diode. By the next lecture, we shall be practicing a simple problem based on this diode. I hope you enjoy the learning with the microwave engineering subject. For more detail like this, you can subscribe to Ekeeda channel. Thank you.